Good morning or afternoon, depending on where you are catching us from. Welcome to another edition of the Relatorium Seminar. I'd love to welcome specifically Dmitri Tymoczko for honoring us by his presence, and I really look forward to hearing about his journey connecting mathematics with music and to listen to some music as well, which he promised to share. So take it away, Dmitri.
Okay, thank you very much for inviting me. Let me see, I'm going to share my screen because I have a PowerPoint here. Hold on, I'm going to share sound and I'm going to start my... Okay, Ted, can you give me a thumbs up? Can you see my screen? Are we good?
Yes.
Okay. Yes. All right, so my talk is about music and symmetry. And we're going to start with some musical background. Why is music interesting from a mathematical point of view? Or maybe a psychological point of view. Music provides many interesting examples of cognitive maps. These are non-trivial geometrical spaces that are internalized by human actors and used in cognition. Music also provides many interesting examples of symmetry. Many of the cognitive maps we deal with in music are quotient spaces that arise by folding up simpler spaces. So you identify points and paths in the space that are related by symmetry. So what I would say in general is music is interesting because it's a place where very abstract mathematics, things like orbifolds and groupoids and fibered categories, connect with very concrete facts of human experience. And so that's kind of unusual. You often see exotic mathematics, in the context of like particle physics or string theory, but music gives us these really concrete examples that are accessible to anyone with an instrument. It's interesting because it provides a test case for geometrical and spatial models of human cognition, which are a growing topic. Let me just cut to the chase and tell you what I'm going to be talking about, just so you have a concrete example for the rest of the talk. Here is a very simple musical space that contains three major chords, C, E, G, three minor chords, E, G, B, and its rotations, and one augmented triad. And the space is symmetrical under reflections along the dotted lines, which turn music upside down or rotate music. We call this transposition and inversion. The question is, how do we fold up the top space to get the quotient space on the bottom? So on the bottom here, we have one object representing major and minor triads, and it's got six loops that represent the six ways of moving around the circumference up here. And then we've got another object representing the augmented triad with its six loops, and this thing is called a groupoid. And we would like to take this simple space at the top and fold it up to get the more complicated space at the bottom. And this is kind of general. Yeah.
Can I ask you a question? Just a very general question for people who might not be as familiar with the music. So these are meant to be essentially somewhat equivalent or somewhat like nearby musical objects that sort of our cognition interprets, alternates between, or something like that.
Well, so to put it very simply, if I gave you, if I presented each of these as a chord or a harmony, and if I gave you a path in this space, and then you went away for an hour or two, and I gave you a rotationally equivalent path in the space, you would probably not be able to tell that I had rotated the space, because unless you have absolute pitch. So these things, they are equivalent, right? And then the reflection is not, the degree of equivalence is somewhat less, but you can think of them as versions of the same thing. And the key point is, in the middle here, we are absolutely fixed under the different symmetries of the space. So you can think of it broadly as we've got a bunch of different mammals up here, and then down here, this is the category mammal, right? So we're trying to make a model of generalization. We're forming a kind of equivalence class. We're creating a concept, right? So there's a geometrical model of concept formation. It's obviously pretty relevant to things like machine learning, which are essentially taking spaces up here and forming spaces down there. Now, believe it or not, human beings do not have a very good answer to my question, how do you fold up this top space with 7 objects to get this bottom space with 2 objects? This is not something that is in the math textbooks in any kind of a digestible form. Funnily enough, if you're imagining a continuous space up here, what's called an orbifold, we do have an answer to this question. So we know how to make these quotient spaces in the context where these are points in a continuous space and we're folding up a 2D plane. But that's kind of counterintuitive. Why should the rest of the points affect our ability to do it with this subset of points? Like ideally, if we can do it with the whole plane, then we can do that same thing to this subset of the plane, or we should be able to. So there's a kind of mismatch between available mathematical tools and our non-mathematical needs, and that's what I'm going to try to answer for you. And by the end of this talk, I'm going to show you how to make this quotient, and more importantly, how to think about it, so you can intuitively understand what it's telling you.
May I also say that it feels like each arrow is doing the same type of transformation, right? It's not just
exactly
a random arrow. It's just a particular kind of transformation that gets repeated as you go along. So
there's some kind of general symmetry. Yes, the symmetry applies both to the objects and to the arrows. Okay. And then the thing that I want to really alert everybody to, because this is important, is that there are 3 different things that we mean when we talk about the quotient of a space by a group of symmetries. These are my names, but there's what I call the poor quotient. And the poor quotient essentially erases all information about symmetry-related objects. So down here, we take all of these circumferential objects and we make one object out of them, and we just have the identity arrow. There's nothing we can do to it. And then we do the same with this middle object, and we know how to make this thing. And then we just have one way to go back and forth. So we've really erased all the information about the symmetries. There's something... So we form a trivial space with 1 point per orbit of the symmetry group. There's something more interesting, which I call a rich quotient, where we actually retain relative information about the symmetries. So we retain the ability to say that we've applied some kind of symmetry transformation, but we lose the ability to know exactly where we are in the space. And that's the thing that I would like to figure out how to make. Geometrically, we outfit the poor quotient, this trivial space, with a copy of the symmetry group at every point. And so that's the thing that we're trying to make. This is what an orbifold does in the context where you have a Euclidean space up here and you form a quotient. And then there's a middle class quotient, which is in between these. You have some subgroup of the symmetry group that's sitting over every point. And that's not a big deal, because if you can make the rich one, you can make the middle class one by just taking some further quotient.
So Dmitri, for musically minded people, I mean, is this what you have in mind when you were talking about the rich symmetry, is where you retain information on the form of the triad, like the 6 or 6-4 form or whatever, like the
it's not quite that. What you do is you actually you retain information about the transformations. So you might not know what form the triad's in, but you can say, if I was at 6, I've gone to, if I was at root position, I've gone to first inversion.
I see.
So you retain information, and this will all become clear, but you retain information about motion. Okay. The point is, these things show up all over the place in mathematical and non-mathematical life. They show up in philosophy when people talk about taking the quotient of a physical theory by its group of symmetries, but we don't really have a good vocabulary for discussing them. And it's kind of important that we be able to do this, because quotient spaces give us this powerful mathematical model of generalization. And especially right now, we're facing these machine learning algorithms that actually seem to do some kind of generalization. And everybody wants to figure out, what are these things doing? Okay, so that's what I want you to keep in mind. And now I'm going to do some fun musical stuff, if you're ready. Everyone ready for fun musical stuff? Okay, so here is an example of a musical map that we have internalized. This is the space of all the different kinds of 3-note chords. The major chord is right here, the minor chord is right here, the augmented chord is right here. Mathematically, it is the space of 3 points on the circle modulo rotations. And you can actually build one. There was or is one at the Museum of Mathematics in New York City. each of these balls is a theremin, so you can actually touch it and hear that type of chord. So you can actually play this geometrical model of all the possible chords. And now this thing is not just a cone. It's not a Euclidean cone. This is a orbifold singularity. It's a cone point. This boundary down here is made of mirrors. And so this thing has a lot more paths in it than a Euclidean cone has, and that each of those paths has a musical meaning in terms of how you move your fingers on the keyboard. So that's an example of the kind of cognitive map that shows up in music, and that musicians, they learn their way around this space under a different guise. All right, so that's my first example. Here's a second fun example. This is a computer language for programming musical patterns called Arca that I made. And so this is a little bit of Arca code. I declare some objects up here, and these are like tracks, and I apply some transformations to the objects. And if you go to my website and press run, you enter this code into the website, and press run, you hear this. All right, everyone heard that, right? Ted, thumbs up. You heard the music? Okay, so that's a chunk of a Beethoven string quartet. And so I lied. You actually hear a crappy MIDI version of that if you press run on my website. That's a professional string quartet. But the point is, and also, it's only approximate that I cut a few corners in the name of making a shorter computer program. But the key point is my program produces this chunk of Beethoven's music. Now, I should not really be able to do that because I have only a very limited set of algorithmic transformations and a very limited set of objects. The only explanation for why this short chunk of code produces Beethoven's music is that Beethoven was running this code in his brain. Otherwise, you have a kind of miracle, right? There's no explanation. What's kind of cool here is that all these commands that I'm applying to the musical objects are loops in one of those quotient spaces. They are paths through a complicated non-Euclidean space. So to say that Beethoven was running this code in his brain is also to say that Beethoven was making certain kinds of moves through these non-Euclidean singular quotient spaces, right? And so that's cool. And it's cool that we have this algorithmic representation of what's going on. And if you want to play with this, my website, madmusicalscience.com, you can just go and experiment with this thing. And my student and I were making musical software that makes this kind of thing much more user-friendly. Does anyone want to ask a question there before I move on? We have one more fun musical object and then we're going to do some less fun math.
So
any questions? Yeah.
I was just gonna, I don't know if it's appropriate here, but in terms of understanding a little bit the higher level structure, you set up a scale and then you create a series of chords and then you transform them. So these T7, T4, and so on, these are transformations to the original sequence of chords in that scale. Is that right?
Yes, so basically that's right. I have a scale, I have a motive, which is a musical pattern. The motive lives inside the scale. I have an accompaniment that actually lives inside the motive. And then everything is algorithmic. Actually, the next example will help you a little bit understand what's going on. So let me just show you that. Okay, so in music, we have
I do have a question as well.
Go ahead.
I'm Matt Insall. I'm in Rolla, Missouri. It's nice to hear you talk about music and mathematics.
Okay.
Are you familiar with Gareth Loy?
I've heard that name, but I can't.
He created his own language for writing music. He's originally a musician, but he designed one called Musimathics. And I found it in a 2-volume set in our library at Missouri University of Science and Technology. I didn't get to read the whole thing because I was busy doing other things, but I don't remember him talking at all about category theory or topology on
Okay,
any of that.
I will go check it out.
I think it would be nice to check for you to. I think you'd enjoy checking it out. That's why I brought it up. Now
Great.
the other thing
Yep.
is that I'm aware of a course taught at Washington University in St. Louis. I'm trying to remember the professor's name. He's probably retired by now, but he wrote a book called Mathematics and Music. And I read that, but many years ago. And I think I'll look it up and I'll try to get you the author's name soon.
Okay.
But
I think, so let me just say,
I think you might enjoy that as well, or enjoy interacting with him if he's still active. So
okay. I will just say, so there is a lot of material out there on mathematics and music. And in my view, so our problem is not so much quantity as quality. And getting the math and the music to talk to each other is actually much harder than people think. So
I agree. I agree.
Let me.
So I've seen papers in music that talk about set theory, and I don't have any idea what they're talking about, for example.
Yeah.
So
all right, let me show you. Let me show you a thing that I think is kind of cool. So here's a little symbolic representation of a chord change. We have one chord, and then we have another chord, and we've got some arrow that represents it. And then here's something that happens in music, which is you take the notes that are not in the chord and you kind of relate them to the notes that are in the chord. You might say, okay, this note is one semitone below this note that's in the chord. Okay, so you've got your chord change, and then you've got these dependency relations that map the notes that are not in a chord to some chord. Now, if you're operating in set, basically the only thing you can really do is compose these arrows. There's nothing else that's obvious to do. In musical space, a diagram that looks like this over here can be associated with a set of natural transformations. And what that allows you to do is take a diagram that, like this L-shaped diagram on the left, and actually transport the relationship, the dependency relationships, so that they apply to chord 2 over here. So we basically have a kind of parallelism. The notes that are not in chord 1 stand in the same relationship to chord 1 as the notes that are not in chord 2 stand to chord 2. And this is actually something that's really at the heart of Western music making. It's what my computer language does. And now what I'm going to do is, Ted asked, hey, why don't you play some music that you've written? And so I'm actually going to show you a piece of music that uses this idea and illustrates it just kind of heuristically. And the piece starts with this piece that I wrote. You can check the date of the composition there. I wrote it about 50 years ago when I was about 6 years old. So it's the first piece of music I ever wrote. My dad wrote it down for me on, lined paper. I believe it's called The Walking Dinosaur. And it has white notes, and then it has black notes, and it has white notes. And a couple years ago, I found this thing, and I decided I wanted to turn it into a piece of music that I could play for people now. But I didn't want to take my 50-year-old self and kind of start rewriting my 6-year-old self's idea, right? That felt unbalanced and kind of, you can't really have a dialogue with your 6-year-old self in that way. And so what I decided to do is use this algorithm I showed you on the previous page, and essentially I created these dependency relationships. So I said this red note, okay, it's a black note. I'm going to think of it as one step above this red note here, and I'm going to say this green note is one step below this green note, and I created these dependency relations. And what that allowed me to do is define a transformation on the black notes that allows me to pull back that transformation to get transformations on the colored notes, right? So what this is an algorithmic transformation of the thing that is non-obvious. You can sort of tell it's the same kind of thing, but enough changes so that your ear gets tickled by the relation. So I took this piece of music, which I wrote when I was 6, and I generated this new variant on it. And then I created slightly different sets of dependencies, and I created a second variant. And then the final piece, you'll hear the original, you'll hear the first variant, you'll hear the second variant, you'll hear the original. And what we're now going to do is we're going to take this link, I'm going to copy it into chat, and then we're going to all put it into our web browsers, and then we will, I will press, I will count you down 3, 2, 1. So everyone go to the link in chat and load it up, but don't play it. And now I have to tell you about this piece of music, okay? So this is part of my practice that's a little unusual. I got frustrated with writing scores a while ago. I got frustrated with telling everyone what to do exactly. And so one thing I really enjoy doing is I run a kind of guided improvisation where what I do is I play on a MIDI keyboard, and I've written software that takes the notes I play, sends them through the internet to iPads that are sitting on performers' music stands. So we're all in a big room together. I play a chord, the notes show up on their iPad, they know what chord is coming. So it's a kind of guided improvisation. I leave them relatively free. So in this case, I'm playing this little piece, and they are responding. It's 16 string players: violin, viola, cello, double bass. And you will hear the piece is about memory, so you will hear what sounds like an old record of the original composition. Then I play the original composition. Then we hear 2 variants. Then we hear the original again. There's no rehearsal. There's no practice. It's improvisation, and then I kind of edit it afterwards. I think we recorded it twice, and I took the best parts of the 2 recordings. So everyone give me a thumbs up. I'm going to go 3, 2, 1. We're going to press play, and then we'll be back in 4 minutes. Okay? 3, 2, 1, go. Okay, we should be all finished by now. Anyone got any questions they need to ask before we move on to the math?
Dmitri, I'll point out, maybe this resonates with others too. To me, it was very apparent, this transformation that you were talking about. This really helped sort of exemplify what you were talking about, both melodically, like how you were shifting, how the theme kept shifting, you leading the improvisation, and then how the harmonies were also shifting in a not algorithmic way. I wouldn't say algorithmic, but in a almost like, like a step up or a step down. Like you could sort of feel like the new frame appearing. And I found myself wondering if in a broader setting, something equivalent can happen, for example, with the rhythm, let's say, or with another aspect of the music, like maybe the orchestration or the counterpoint or something, the shifting frames.
So the first thing I'll say, so it actually is algorithmic. And the trick is that the algorithm is complex enough so it feels organic. So the sweet spot is to find something where you can tell that there is structure, but you don't know what the structure is. When the structure, so if it were a simpler algorithm, you would hear it and it would sound less organic and more boring. The question of what symmetries apply to rhythm and other parameters is really interesting, and I'm going to defer that to the end of that. That is an ongoing question. So, okay, the only thing I like this piece, I'm proud of this piece. What's interesting about it is it lives in a very strange spot. It is algorithmic, it is improvisational, it's technological, it's organic, real people are playing it. And so it's the kind of 21st century mixing. These ideas are very old ideas. Beethoven would understand what I'm doing with these dependency relations. But knowing that you can take those Beethovenian techniques and apply them more generally, that requires a little bit of contemporary musical insight. And I might be one of 10 people in the world who thinks about music in such a way that these colored arrows are a very natural thing to do. It's not everybody has taken those ancient techniques and sort of reworked them so that they become general 21st century tools. So this is the kind of thing I'm chasing after. All right, now we're going to do some math. Everyone ready? I'm not a mathematician, so I will make plenty of mistakes. One of the things I think is incredibly cool about contemporary mathematics is it gives you all these different ways of looking at one and the same structure. So in particular, we can start up here with a geometrical space. We can forget distance information and get a topological space. We can forget the open sets and the topology and form the fundamental groupoid, which gives us, something much more abstract. You can think of it as a homotopy 1 type. And then we can forget the groupoid structure and end up all the way down here with a category, which is a kind of purely algebraic object. Now, this kind of forgetting of structure is pretty obvious, and it's always available to us. What's a little less obvious is we can go the other direction, right? So we can start with a category, and we can form what's called the groupoid completion, which is, sort of there's a nice categorical limit where this is well defined. So we can take a category, turn it into a homotopy 1 type, then we can form what's called the geometrical realization and get a topological space. We can assign a metric, and so we can climb all the way up from the very abstract world to the more geometrical world. And so being able to navigate this space of possibilities is something that contemporary mathematicians know how to do, but applied folks like me don't usually know how to do this. Okay, quotient space glues together points and paths related by some symmetry group. Because all of these are very symmetrical spaces, we can form both rich and poor quotients in all of these different levels. The quotients create connections between levels, and this can be really confusing. And I would like to give you a very simple example that's central to music. So musical pitches, notes, They live on the geometrical line, which we can just think of it as R, the real numbers. Every real number, you take the logarithm of the fundamental frequency, that gives you this nice real line. Okay, we have to approximate a little because the real line is infinite, whereas pitch perception is bounded, but we're not going to worry about that right now. Now, notes that are an octave apart sound similar, right? This I call Maria's theorem. T takes us back to do, okay? So you go up far enough, you end up back where you started. And so we can think of this as a kind of helical structure, wind the line into a helix, and then we can form a circular quotient space, which musicians call pitch class space, by gluing together octave-related points. And all of this is just very familiar topology, right? We're just taking the quotient of the line by some group of translations and we get the circle, and everybody knows about this. Okay, now where things get tricky is that in the circular space, homotopy classes of paths at a particular point can be modeled by real numbers that give you the distance from the first pitch to the second. So for instance, 0, if I start here and move by 0, that homotopy class takes me back to the pitch that I started. But if I wind once around the octave, that actually moves me up by octave. If I wind clockwise around the circle, if I wind the other direction, I move down by an octave. All right. So the homotopy class that groups paths into categories that all share the same winding number, and that winding number can be interpreted as a change in octave. What that means is that when we hear a pair of pitches, which is a pair of points in the original linear space, that pair of pitches gives us a homotopy class of paths in the quotient. So these blue notes here involve C moving up to E by 4, and that corresponds to this homotopy class of paths where I move from C to E by the homotopy class that includes the 4 semitone ascending motion. Meanwhile, the green guys go from C to E down by 8, and that corresponds to this homotopy class of paths. And this one red guy moves up by 16, and that corresponds to this homotopy class of paths, right? So what's confusing here is that pairs of pitches, they don't give us specific paths in the space. They also don't give us just pairs of points in the quotient space. They give us something else, something that has as its most natural description a topological concept, a homotopy class of paths, right? So what's confusing is we started up here in the geometrical world, but we actually ended up down here talking about fundamental groupoid, arrows in a fundamental groupoid, right? So this is very elementary. You can explain it to a high school student, but it is conceptually confusing because if you decide ahead of time that you're going to stay at one level, like I'm going to model music geometrically, right, you might be in trouble because the most natural models might actually not be geometrical models. They might live down here. And if you don't know how to move around these different levels, you can end up somewhat confused. There are a lot of cognitive scientists. There's a guy named Gardenfors who wrote this really interesting book where he uses geometrical structure to model cognition, right? But he ends up postulating a lot of geometrical things like lengths and angles and so on, where I don't think that that's at all justified. There's a big fuss about word-to-vec a while ago where people started talking about analogies as having geometrical structure. A lot of that work is like really naive about asserting that there's more geometry than there is. So things go wrong when you get fixed at a level and you don't want to leave. Yes, go ahead.
I wonder if one way to understand this transition you're trying to make here is as a means of as a filter that helps us focus on what is important. Like there's a level at which even in music, let's say, the particular octave may be important, in which case you live in that, more detailed space, let's say, right? Like, but then there is a level where you quotient out that symmetry, in which case really what matters is the homotopy, as you say, of the movement where you move up or down or how many times you wind, in which case, in other words, it's a shifting frame that focuses your attention to a particular aspect.
Yes, I think that's exactly right. What I would say, though, I would say two things, right? The first thing is the shifting frame also, you might think that the quotient leaves you at the same geometrical level. And in this case, forming the quotient starts to focus you on things that are topological. So
right,
and then secondly, when people have thought about these quotients, they've thought about forgetting octaves completely. But the important thing about the homotopy classes is they give you relative information about changes in octave. So there's a difference between going up an octave and going down an octave, right? So you lose information about exactly where you are in the space. You lose absolute information, but you retain relative information about the very thing you're quotienting out, right? You're quotienting out by octaves, and yet you're retaining relative information. Let me show you another example of this same thing. Okay, let's think about equivalence classes, all right? So an equivalence class is a logical concept, and we can model it using a pair groupoid. So we have a bunch of objects, and then we've got one invertible arrow for every object in the space. So here I've got a 6-object equivalence class. All the objects are mammals, and I've got kittens, puppies, and kits, which are baby rabbits. And then I've got adult cat, dog, and adult rabbit here. And I've got an equivalence class with those objects in it. And you can think of the arrows as isomorphisms. Maybe they map the analogous part of one thing to the other thing, okay? Now, a functor from one equivalence class to another creates analogies. So in this case, I have a functor that projects to feline, canine, and leporine. I've ignored age, and now I've got a whole bunch of arrows up here that map to an arrow down here, and we can think of this as making an analogy. Cat is to dog, as kitten is to puppy, as kitten is to dog, as cat is to puppy, and that's all that arrow there. We've actually here quotiented out by all information about age, right? Because cat and dog and kitten and dog are the same arrow. In much the same way, we can project in the other direction, forgetting about species and remembering only age. And now these arrows here are pretty large equivalence classes, right? So cat is to kitten, as cat is to puppy, as cat is to kit. The only thing we're remembering is age. So we can think of functors as creating analogies, and that's kind of cool. The fibers of a functor are the objects and the arrows that are mapped to the identity. So in our first functor, the fibers look like this. They relate adult and child mammals, and they include the isomorphism between them. Over here, the fibers look like this. They relate mammals of the same age, and we've projected over here, okay? So now a discrete fibration is a kind of cool category theory thing where the fibers contain only identity arrows. So here's another way of projecting onto species, but now each species has 2 arrows, a dotted arrow, and there's a dotted arrow linking the species, and a solid arrow. The solid arrows preserve age, and the dotted arrows change age. Here's what the fibers look like. The fibers are only the individual objects with their identity. And the cool thing about a discrete fibration is it has a maximum number of analogies, each of which is maximally specific for a given object mapping. So in this case, each arrow down here corresponds to exactly 2 arrows up here. And the analogies are cat is to puppy as kitten is to dog. This is an age-changing transition from feline to canine. You lose track of where you are. You don't know if you have an adult cat or a baby cat, but you know that whatever the age of the cat you started with is different from the age of the dog you ended up with. So this is a quotient that retains relative information about age, even while discarding absolute information about age. So discrete fibrations are a kind of categorical limit for a given object mapping. What's kind of not obvious is that a discrete fibration arises if and only if an equivalence class has a symmetry. In this case, we have the change age symmetry that maps this equivalence class onto itself. So discrete fibration is a quotient groupoid formed by gluing together symmetry-related objects and arrows. Here's what it looks like. These are all the arrows that are glued together. I think of them as enriched equivalence classes where you have multiple isomorphisms between the objects in the equivalence class. So in this case, the feline and the canine objects have two separate isomorphisms, one of which is age preserving and one of which is age changing. Once again, as in the original example, a pair of points in the original equivalence class determines an arrow in the quotient. So if we have cat and puppy, we can say, that's this dotted arrow here, the age-changing arrow that connects feline to canine. Same thing if we have kitten and dog, same arrow. So the arrows erase the absolute information about age while preserving the relative information about changes of age. Now, this is basically the same example as the pitch example I started with. They are the same logic, same structure, except we started down here and we're sort of living in the abstract category theory world. But if we want, we could make a topological space out of this thing using standard techniques. And if we ended up here, we have a geometrical space and we can interpret the points in this space as probability distributions over objects in the equivalence class. So you can think of them maybe in a Bayesian context as the probability that we've got one kind of object or another, or any situation where you want to assign probabilities to this thing, that would be the geometrical realization of this abstract structure. Okay, so what I want to do is understand this universal thing. Just let me finish this sentence, and then I will stop. And then we have one little part. So I want to understand this very general structure, which, this is a dumb example with rabbits and cats and whatever. But the point is, it's recognizably the same structure we encounter in music, and we don't really have a great framework for articulating it. And that's my goal. Go ahead, Ted.
Yeah, no, sorry. I just wanted to connect with the earlier point you made, the connection with AI in particular. And it seemed to me that maybe essentially this last thing you were talking about is effectively the space of current like LLM instantiation of AI, where they're looking at the probability distributions, essentially the nearness of probability distributions of various instances. But perhaps, and this is my question to you, is if you think that maybe the semantic space, the space of the meaning that matters to us, might be more in this sort of abstract space of the homotopies around them, the things that remain invariant and the encoding that we have in mind when we say anything.
Right. So this is a real. So I don't have a real theory here, but what I will say is that one of the nice things about the category perspective is that a neural net is very close to a category. It looks a lot like a weighted category, right? And it's pretty clear that LLMs are generalizing, and so so what they are doing is they are making some kind of quotient spaces out of these categories that are like that represent neural nets, right? So I think that generally speaking, there's no question that what LLMs are doing is some kind of generalization by forming quotient spaces. And yes, I generally think that in a lot of cases, we want to be talking more topologically than geometrically about the structures, but it's a little bit of a mixture. Like sometimes we really need to be able to go back and forth and realize there's not a once and for all choice, but you need to be flexible and sort of understand when you've got a more topological kind of situation and when you have a more geometrical situation. All right, I've got one more little part and then I'm going to stop talking. So I want to give you what I think is the actual, there's a helpful idea coming. So let me start with this great quote by Bill Lauvier, who's, an important category theorist and a bit of a visionary. He said, the technical advances forged by category theorists will be of value to dialectical philosophy, lending precise form with disputable mathematical models to ancient philosophical distinctions such as objective versus subjective. And, Lauvier, he earned the right to say kind of mystical things like this because he did so much important work. And you look at this and you're a little bit like, okay, yeah, whatever, maybe. I think there's a sense in which he's absolutely right, and I'm going to try to explain, it's not mystical at all. So suppose we have any space with any sort of symmetry. So this diagram has a reflectional symmetry around its horizontal center point. We form a quotient space by gluing together symmetry-related points and paths. In this case, our symmetry operation is fold the plane in half. It forms a two-element symmetry group. The other element is the trivial operation that does nothing. A rich quotient contains a loop for each symmetry. So in the rich quotient, we have some kind of loop that corresponds to move to the other half plane of the figure, right? In geometrical contexts, this might arise if you've got ordered pairs and you're folding them up to get unordered pairs, and then your loop would correspond to reorder the pair. So you don't know what order the pair is in, but the loop tells you you've just changed the order, okay? In the pitch case that we looked at earlier, the rich quotient has these loops that correspond to moving by octave. In the mammal case, the rich quotient has these loops that correspond to changing the age. So in each case, we have a loop that changes, that corresponds to the symmetry operations that we quotiented out by. So you can think of these spaces as erasing absolute distinctions about symmetry-related points while preserving relative information. The poor quotient has no loops at all, so I've just erased all the loops. You have completely erased the distinction between symmetry-related points. So we've got these two kinds of quotients. Let's take the example, fold the 2D plane in half. We've got a poor and rich form of making quotients, but then we've also got these different levels from geometry down to algebra, geometry topology, category theory, right? So you might ask, how do these two forms of making quotients appear in these different contexts? In the geometrical context, the poor quotient gives us just the half plane, a manifold with boundary. Its fundamental group, FG, is just the identity. You fold the plane in half, you get a manifold with boundary. It doesn't have any interesting, topological structure. You can form that same quotient in a topological context. If you read Ron Brown's book, Topology and Groupoids, and you look at what he calls the orbit groupoid, it is the poor quotient, but now expressed in category theoretical language. On the other hand, we have a notion of an orbifold that tells us how to form the rich quotient in a geometrical setting. So we take the plane, we fold it in half, and now we get a structure where you have what's called the orbifold fundamental group. You have non-trivial loops at each point, and these correspond to, say, reordering the points in your unordered pair, and these are the things that show up in music. The interesting thing is we don't have a standard analog of that in the topological context. It's kind of a pain in the butt to create this thing and describe what the open sets look like. And then we don't really have a great way of talking about it in the category theoretical context either, but we should. The whole philosophy of being able to switch levels tells us we should be able to have the topological or the category theoretical analog of this quotient. It should be somewhere, and it isn't. And the real problem is fixed points, okay? So it's really hard to conceptualize these rich quotients using the tools of classical logic and classical topology when you have a symmetry group that fixes points. And paradoxically, it gets harder and harder to do this the simpler your examples are. If you're doing scheme theory and you're way off the deep end in algebraic geometry, then you're not worried about the kinds of questions like what exactly am I talking about here, because you have accepted that you are living in such an abstract world that maybe certain intuitive questions aren't going to have answers. But in my world, you need to answer those questions. And the real issue is it's very hard to interpret the duality between symmetry operations and fundamental group sort of loops in the quotient, fundamental group elements. It's really hard to interpret those in the presence of fixed points. And now I've got an example that hopefully will illustrate all of this. So down here, I have the group of permutations of three objects. These are the three swaps. Here are the cyclical permutations. And I'd like to be able to conceive of this as the rich quotient of some equivalence class of some pair groupoid. And so we know what the parent space, what the covering space should look like. It should have 6 objects up here, and they should all be related by the permutations. This thing should be a torsor or a principal homogeneous space for this thing, okay? So here's my equivalence class. Here's my rich quotient. I want to form a discrete fibration. we kind of know what we should do. And then up here, we want to glue together all the arrows that represent the same permutation. So actually the short arrows here represent AC, the long arrows represent AB, and then antipodal motion would represent BC. Okay. So we want to take the quotient by the group of permutation preserving isomorphisms, the symmetries. The question is, what do those symmetries mean? What are they? In other words, how do I fold up the top space to get to the bottom space? How can I characterize the actions that relate the arrows representing the same permutation of foldings, right? We kind of know on general principles that the symmetries need to be dual to the fundamental group elements. So if we think of this as a left action of the symmetry group on the objects A, B, and C, then the folding operations up here are the right action of that symmetry group on those same objects. The problem is that the fundamental group elements down here contain all the isomorphisms of A, B, and C. So there's nothing left for the symmetries to be. They can't be isomorphisms of A, B, and C because they are all used up. All right, so we're kind of toast if we want to explain what the symmetry group actions are up here. Okay, so mathematicians have a lot of ways of answering this question. That you can do it, but you can't do it in a way that is musically useful. And so now what I'm going to try to do is I'm going to tell you how I do it, and I think it clarifies this territory, and then I will be done. Okay. To do this, I want to have a little bit of a digression, and I want to ask the question: how do we model the perspective of a point-like being in a space? We've got a point-like being in an abstract space. And you might think, oh, well, that's really easy. All we do is we pick out a point in the space that, we just, we declare this point to be its position. It turns out to be better to model the perspective of a being in a space as a map between the objective points in the space and a subjective set of distances and directions, which you can think of as coordinates. And here's a little picture. Okay, I got my XKCD guy here. These numbers give us the objective points in the space. My orientation in the space assigns a subjective coordinate to every point in the space. So the objective point 0, 0 is my location. -1, 0 is 1 foot in front of me. 0, 1 is 1 foot above. This is a side scroller like Donkey Kong. So we have an up and down and left and right. All right. And then if you change your orientation, you change the map. So what I've just done is turned around. My location has stayed fixed, but now 1 foot in front of me has moved from, it used to be here, and now it's here. So to model the perspective of being in space, we actually want an isomorphism between what I call elements, those are the points in the space, and what I call attributes, which are a coordinate system that represents the subjective relation of those points to me, okay? So what we really want is not a functor, not a point in the space E, but a point in the mapping between subjective attributes and objective points. We pick out a specific location as here. Maybe we want 2 points. We can pick out one location here and another as, this is in front of me. Maybe sometimes we might need multiple attributes to really nail down the configuration of a being in space. But the key idea here is to model a being's position in space. We don't want to just look at the space itself. We want to look at an isomorphism between a set of attributes and a set of elements. And then we want to pick out a set of attributes that determine our position. So in this case, we might say, I am at point 1 looking toward point 2. And in the simple cases, an attribute element isomorphism is just an ordering of the elements, but sometimes we might have a 2D space and it's not just an ordering, right? Okay, so this actually answers our question about how to think about symmetries and intervals in this case. What we want to do is replace the unordered set ABC, that's our set of elements, with an attribute element isomorphism, which is to say an ordering of those objects. Then it's totally clear. Every arrow here can be interpreted either as a attribute permutation like AB, or sorry, an element permutation like AB, or an attribute permutation like swap the first two items in your ordering. And then you have this very nice duality. The symmetries are the permutations that act on order numbers, and the intervals, the fundamental group elements down here, are those same operations, but now pulled back onto the elements. The thing that's tricky is that the logic of the situation has forced us to expand our ontology, right? And so you might have thought your problem was just a problem about these three objects, A, B, and C, but secretly your problem is also a problem about the numbers 1, 2, and 3 and mappings between A, B, and C and 1, 2, and 3. Okay, now here's the cool thing. You can generically interpret attribute permutations as representing the subjective actions of a being in the space. So if I am at 1 looking at 2, then the attribute permutation 2, 3 corresponds to the action turn around. This is turning around and it's swapping 2 and 3. Okay. Similarly, the attribute permutation 2, 1, 3 corresponds to move forward, right? So generically, once I've picked out a set of attributes that determine my position, then the attribute permutations correspond to subjective motions in the space. In this case, turn around and move forward generate the whole permutation group. Go back to that Levier theory, that Levier quote where he was mystically talking about how category theory was going to, connect to the subjective-objective distinction. I'm now going to enunciate what I modestly call Dmitri's law. It's just a joke, really, but if we have a group of objective symmetries acting on the points in a space, then the associated rich quotient can generically be interpreted as a set of subjective motions available to a being inside the space. And so this comes up in music. In music, we have objective transformations that act on chords, say, and then we have a set of subjective transformations, which musicians have called contextual transformations that can be interpreted as transformations available to a being that lives inside the space. The objective versus subjective duality is exactly equivalent to the one and the same set of transformations operating on two sides of an isomorphism, where one side is the objective side and the other is the subjective side. Physicists call this active versus passive transformations. This duality has all these different names in all these different fields, and what I'm trying to do is situate it at this very abstract category theoretical level. It's really universally true. My favorite example, take the group of 2D rotations and translations, the special Euclidean group in 2 dimensions. You can imagine that acting on the points in a space or on a map. We can rotate the map clockwise. We can slide the map, east, west, north, and south. Now, how do we represent a being in the space? Put a translucent sheet on top of the map, draw an arrow representing your perspective. The tail of the arrow is where you are. The head of the arrow is where you're looking. We pull back those rotations and translations so they're operating on the translucent sheet. They're now generated by 2 different transformations. Rotate my viewpoint X degrees clockwise and move forward by X degrees. This is very similar to what we saw in the permutation group where we had turn around and move forward, but now it's operating in this continuous group that we're very familiar with from daily life every time we use a map. Over here on the left, I call this the map group, right? It's acting on objective points. Over here on the right, I call this the turtle group. It's the same group, but a different group action. Why do I call it the turtle group? Because this is what's going on with turtle graphics. It's also what's going on when you open Google Maps and there's a blue dot in the center of the screen and a little wedge that shows your viewpoint, and that blue dot stays fixed and the world rotates around you. Going back to the first example I showed you, you can interpret the arrows over here as representing things like rotations for this symmetrical chord here. So there really is this funny universal subjective-objective duality that plays a role in forming these rich quotients. Now, I think you can make a compelling argument that attribute and element isomorphisms are necessarily present in any real world instance of symmetry. So this ontological shift where the attributes appear, I don't think that's putting anything new into the situation. I think the attributes are already there if you look carefully enough. If you try to conceive permutation without both elements and attributes, something goes wrong. But I'm not gonna press that philosophical point here. What I just want to say, this attribute element isomorphisms, this gives you a low cost, very intuitive way to understand fibered categories and something called the Grothendieck construction. This is what you need to work with rich quotients. These things show up all over the place in musical and non-musical life, Google Maps, working with a map. There are lots of people who know tons more math than I do who have managed not to notice the ubiquity of these constructions. And I think this is because their formalism is too complicated. They think about fibered categories in a more abstract way that doesn't allow them to recognize instances of fibered categories when they encounter them. One of the cool things about music is we can't afford abstraction, right? You can't stop the music, get your pencil and paper, and work out what the music is doing. We have to have intuitive ways of understanding what's going on because music is real time. It happens too fast for pencil and paper. So paradoxically, the very simplicity of musical examples forces us to kind of distill certain mathematical concepts to the point where maybe they become useful in new ways. That's all I have to say. I have these two books. You can go to my website if you want to learn more. Thank you very much. I will stop sharing.
Well, thank you very much, Dmitri. First of all, let's thank our speaker. Hold on, where's the reactions here? Let's see. Yeah, this has been a fantastic tour de force. I mean, you really got us through so much material.
Right.
And I know from our earlier interactions that you wanted, a venue to sort of share these mathematical thoughts you had and maybe be pushed back and sort of, but I think the words you ended with are very close to my heart as an educator, mathematician, but one who's focusing mainly on communicating mathematics to a broader audience. I really resonated with what you said, that in some sense, to put it differently, but it's this intuition that we want to develop through various practices like the musical practice you're demonstrating, to sort of intuit the points of the formalism, to have the formalism help us make sense of what's going on as it's happening, rather than the more contrived or constructed sort of labored view that we're often shown or see in classes, in formal settings, where we kind of we focus too much on the formalism and all its attributes, rather than see it arising organically or practice sort of the intuitive sense of what is going on. So I think music, especially if you get, I wonder if you can tell us more about this, but I wonder if you can kind of train your ear almost to hear, the quotienting, to hear these, so to put words almost in this sense that we were having when we listened to your piece, for what those transformations were like, and to say, this is what's going on. This is an orbit, kind of, clockwise or counter, or whatever it is that makes sense to you, and to be in the lookout for that, so that it elicits a deeper understanding.
Yeah. Let me actually, so there's a really good example of this. So one of the main symmetry groups in music is the dihedral group, right? So you have translations that are moving the music upside down, and then you've got reflections that are turning the music upside down, right? And so an absolute reflection moves points by very different amounts depending on how far they are from the fixed point, right? So if you're just above the fixed point, you go just below the fixed point. But if you're a mile above the fixed point, you go a mile below the fixed point, and that's a 2-mile transformation. So that form of reflection on the one hand, it's useful because it allows you to take a whole piece of music and turn it upside down, and the very high notes become very low notes, and that's great. But it's also a little bit counterintuitive because it can be hard to recognize, okay, is this note that just moved by 2 miles, did that move upside down, right? So the dual of that group, the dual action, so let's just stipulate what I just described is the left action of the dihedral group on notes, right? So you might ask, well, what's the right action? Well, the right action in the case of reflections is extremely intuitive. It takes a major triad and lowers its minor third by 1 note to form that very minor triad. So if you've got C major, it turns it into C minor. And if you've got G major, it turns it into G minor. And whatever major triad you're in, it turns it into that minor triad. And this is the characteristic of these fundamental group elements. They are the same under the action of the symmetry group, right? So it's the arrows that are being related by symmetries, right? So that's the most natural thing in the world. Any major chord turning to that very minor chord is immediately perceptible and is immediately musically relevant. So this is an interesting example because in the case of the dihedral group, the translations are maybe a little more intuitive when they're the symmetries, but the reflections are a little bit more intuitive when they're the fundamental group elements, right? And yet those two things belong to different groups. They're actually playing different mathematical roles. So I would say this fact has caused a tremendous amount of confusion because sometimes people want to take this intuitive set of transformations and this intuitive set of transformations and glue them together to make a group. And it can be very hard to see why that's not a good idea. It's in this case, it's better to keep them separate because if you really understand the whole lay of the mathematical land, you realize, okay, no, this is the dihedral group acting on objects. This is the dihedral group acting on subjective coordinates. But understanding that comes way down the line after you've done a ton of mathematical modeling and is not apparent when you just sort of sit down and pick up your pencil at first. But so that's an example of a homotopy class of paths. Lower your third to turn major into minor. That's immediately intuitively apparent, and yet understanding the role it plays in the big picture takes something like the ideas that I've been talking about. I'm open for more questions if people have.
Right.
Yeah,
Anybody else have questions, please? Yeah.
So I wrote down something. I'm trying to see if this is exactly what you said. Did you say that philosophers quotient groups of physical theories with respect to their symmetries?
Oh, yes, I did. I could talk a lot about that. Yeah. So there's actually a huge mess in the philosophy of science around the topic of symmetry. And so you will find people, respected, very intelligent philosophers, saying that symmetry is saying things I consider absurd. For instance, that any symmetry is a sign of redundancy in a theory. So in the musical case, they would say that there's no such operation as transposing all of music upward by 2 semitones. And this goes back to a debate between Newton and Leibniz about whether it is conceivable to move the entire universe 5 feet to the left. Leibniz was a relationalist about space, and so he said that is an inconceivable thing. It makes no sense to move the universe 5 feet to the left. Newton, I believe, kind of committed the opposite error where he said, no, we've got absolute space, and so we can measure motion relative, like one of the Galilean reference frames is the correct one, and because it's at rest relative to absolute space. So I actually think neither of those views is right. There is probably no absolute space, and yet I think the idea of moving the universe 5 feet to the left is not an incoherent idea. So all of this involves kind of understanding the role of symmetries in, okay, it's hard enough when you want to do it in Newtonian mechanics, but then if you want to do it in relativistic quantum field theory, it becomes really hard. And my suspicion is actually the philosophical problems are pretty similar in the Newtonian and in the relativistic quantum field theoretical case, but in the quantum field theory, your physical theory is so complicated that it just keeps you from actually understanding the philosophical issues as clearly as you need to. But that's a great example, like of it's an ongoing question. I'd say philosophers of physics are like roughly evenly divided between the people who think you can move the universe 5 feet to the left and the people who think you can't do that. And basically, the whole issue revolves around forming certain kinds of quotients. And to my mind, all this, it's really a debate about the poor quotients versus the rich quotients that I was talking about in this talk. And this is an example of, like, to answer this question, you actually need a clear conceptual understanding of what the different kinds of quotients that are generically available in all these spaces are.
Dmitri,
So this is kind of sorry, I had a stupid follow-up, actually.
Yeah, please. Yeah, no, I want to follow up on that as well, but go ahead, you go.
Yeah. So my stupid follow-up is I'm confused how you even imagine moving the universe 5 feet. Like, are you imagining yourself outside of the universe and then moving it somewhere? Or, like,
right. I mean,
moving?
Yeah, well, so this is a complicated question, right? And the reason people have debated it for, 300 years is because there are things to be said on both sides. So I am not going to give you a definitive answer. I believe, so the way I think of moving the universe 5 feet to the left is as some kind of limit that results after you move different parts of the universe 5 feet to the left. So you move it little by little, and then you ask, is it coherent? Let's say I move everybody agrees I can move all of the universe except for one particle 5 feet to the left. In the philosophy world, we all agree that that's possible. And then the question is, when I move that final particle 5 feet to the left, have I gone back to my original state or have I achieved a different state? And that's where everybody disagrees. So I'm not going to say it's an easy question, but, what I will say is that the question involves understanding symmetries and quotients in a principled way. And this is why, we don't know how to form these dumb quotients in music. Music gives us these examples where you've got like 4 objects or 6 objects, and you can kind of write down what the different quotients should look like, but understanding what they mean is a genuine conceptual challenge.
So, but for example, I wanted to make this more concrete for the case of music, this sort of moving of the whole universe. And maybe I'm very, very naive, but I've always known, for example, that the Moonlight Sonata is in C# minor. Why can't we move it to be in D minor, for example? We could shift everything, right? Why do we say that? What does it matter? And maybe it is because of our limited absolute hearing range or something. But what thoughts do you have about that?
Well, so the idea of, so that's a good, everybody, when you translate some of the philosophical ideas into music, like, it's very clear that, when I play it, musical symmetry is very interesting. That transposition in music is translation in space, right? And what's very interesting about the example is that when I immediately transpose the Moonlight Sonata, if I play it in C# and then I play it in D, it's like night and day. You notice the difference.
I know, right? Yeah.
And yet, if you don't have absolute pitch and you come back a day later or an hour later or even 5 minutes later, you might not notice. You're not reliable. If I just randomly play it to you, either in D or C# minor, I mean, you can't tell, right? The definition of absolute pitch is being able to tell, and most people don't have that. So it is a funny case where the symmetry operation is extremely palpable when it happens, and then it sort of fades away relatively quickly enough so that we can see it fading away. So that the D minor Moonlight Sonata sounds wrong at noon and then right at 12:05. And so again, I think it's interesting in the context of some of these Galilean symmetries where they don't have that character, right?
So I had this question earlier from something else you said, and this now reminded me of it. The notion of building and breaking expectations in music composition, in appreciation of music. Like, there's a lot done and said about this in cognitive science, and arguably this is relevant to other parts of cognition, not only music. Just music offers a very nice environment to study this. So it reminded me of what you were just saying, where, we have a certain expectation is built, and then you can notice very clearly where the shift is. So in other words, the expectation serves as the background against which you will notice a shift. But then as soon as you notice that shift creates the new framework, which becomes your new expectation. There's a certain recursive sense to what you were talking about. Is this something you've thought about in the context of music, and how does your framework kind of play with that?
Well, so I'm going to actually back up and do the politicians thing where I answer a slightly different version of the question. What I would say just in general is that up until about 5 years ago, I was really only interested in music. And my second book is very musical and really is about like these dependency relations in Beethoven. And I would say that I had almost no interests outside of music, intellectually speaking. One reason I wanted to give this talk, and something that I'm starting to become more curious about, is the question of how these musical models can affect our thinking about cognition more generally. So I do think music is unusual in that, it gives us these very concrete models. This cone is 3-note chord space, right? That's the type of 3-note chords. So the models are very concrete. They're right there. You can write them down. And we don't have that in a lot of other places. So I like the idea that geometrical spaces and topological spaces are a kind of intermediate. They lie intermediate between the more biological perceptual data we get, retinal excitations, and the linguistic conceptual world that we do a lot of our thinking in. So I like the idea that between the physics of the rods and cones in the retina and the language that forms our internal narrative, there's this sort of middle level of maps and geometry and quasi-spatial structures. I think and Gardenfors is very good. I criticized him earlier, but I think he's entirely right that this is, and neural nets kind of are these quasi-spatial structures, right? So my longer answer to your question is that one of my projects for the next few years is to try to see if I can push some of these ideas more into the cognitive scientific sphere and sort of try to participate in some of these cognitive science philosophy debates about symmetry, where maybe I can take some of my concrete models and say, well, okay, if your theory of symmetry is right, then that would imply this in the musical case. And maybe that will allow us to see some of these old debates in a new light.
I have a question.
Sorry. Go
yeah,
ahead.
go ahead.
The slide that says, now I know how to go on.
Yeah.
The last bullet point was the logic of the situation for expansion of the ontology. That's a fascinating notion. Logic and ontology, that connection, and logic having the power to force that. Can you say more about that?
Yeah, let me just see. I actually have an example of this, and I'm just going to see if I can find my Okay. Yeah. Let me. I think the best way to show you this is through an example. So I'm going to find it and then share my screen. Because okay. So all right. I got it. Let me go to Zoom, share my screen. I'm glad you asked this question because, all right, so here's an example. So I'm going to play 3 notes, okay? These are C, middle C, the E and G above it, and I'm going to use sine waves at the same volume in the centered in the stereo field, okay? So here are your notes. Did you hear those? All right. Now, I'm going to play you some other notes. And let me ask you this question. Did I permute the notes when I play? Right? The answer is sort of like, huh? It's not really clear what permutation means. It's not just like, what would it mean to permute those notes, right? And so as a philosopher, I believe that for any permutation to be conceivable or comprehensible, we need 2 ways of identifying objects. We need the objects themselves plus some other attribute, right? The intuition is permutation means 2 objects have switched places. So for objects to switch places, we need objects and places. So in this case, if I give you this, and then I give you this, and say, did I permute the notes? You say, yeah, because you can intuit that I'm thinking of order as the relevant analogy of place. In the first example, there were no places. It wasn't at all clear what served the role as place. So almost anything, these are what I call the attributes. In this case, the notes are the elements, and then I've got some other kind of data that is attached to the elements. And that's what gives us a grip on the idea of permutation, right? I like this example too. I've got these 2 shapes, right? Let me ask you, does the second one permute the first one? Right? Again, it's a malformed question because we don't understand what the analog of place is. Now, if I give you these 2 shapes and I say, does the second one permute the first one? You know what I'm talking about. Or if I give you these 2 shapes, you know what I'm talking about. Or if I tell you I drew the O first in one shape and the X first in the other one, you can't perceive that, but you at least know what I'm talking about in terms of grounding the notion of permutation. So what I take these examples to show is that when we are talking about permutation, we are surreptitiously talking about not a set, but a mapping between an isomorphism between 2 sets. One is the set of objects and one is the set of locations. So this question, what I would say about forcing the expansion of our ontology, normally mathematicians are pretty cavalier. They just say, okay, imagine a permutation on some set. Okay, great, I've got a permutation. They think of permutations solely in terms of the elements of a set. But what I would say is when you're in any kind of real world applied context, surreptitiously, if you are thinking meaningfully about permutation, then your ontology is actually a little more complicated. You actually do have this isomorphism there. It's just that, like, I don't know, in a lot of mathematical contexts, you can ignore the isomorphism and just talk about the permutations and no harm done, nothing bad happens. But what I think is kind of cool about my problem is my problem forces you to go into this very sort of almost metaphysical question, what do permutations mean, and forces you to recognize the existence. Well, permutations involve objects switching places, so I need objects and places. And once you have both of those things, then you can actually make these quotient spaces in a perfectly coherent way. So that's a long answer, but it is, I think, a really important question. And I would say the ontology is already there. We just were discarding parts of the ontology because it wasn't relevant. And what's precisely cool about the stuff I've talking about is it's a point where suddenly you can no longer afford to be cavalier about that aspect of the ontology.
In real world situations, ontological shifts and ontological differences have cataclysmic consequences. When people foresee fundamental change that implies a change in the world, that can be very, very, very disturbing. And for you to speak mathematically about a complex real world situation, I may be forcing things a little bit here, but I just find that fundamentals are not easily engaged by people in everyday life, especially when you're dealing with social justice issues. And a lot of the bias and discrimination is based on presupposition about being, the being of people. What are they essentially? So when you try to understand notions of being and other abstract concepts in a way that breaks them down and maybe shifts them from a concrete to an abstract level, it helps people not be cavalier about their assumptions and presuppositions and so forth. So I think your work is very important to me, at least on that level.
Cool. Well, thanks. Other questions?
So I had some connection problems and so forth, but now I'm reconnected. And I did have a question about your slide where you talked about going back and forth between the with the quotients going from using forgetful functors and then going back. It's the going back that I had a question about.
Mm-hmm.
So I don't see how you quote go back on some of the levels. And you said that was something people don't seem to see. So I don't know quite what you mean by going back whenever there are topological spaces that are not metrizable. So how do you go, for example, from topological spaces to metric spaces?
Right. So yeah, this is out of my expertise, and there are certainly some topological spaces that you can't do this with. Okay.
Okay.
But
okay. Yeah.
So in my neck of the woods, my topological spaces are all very well behaved. So these kinds of things are not a problem for me. Generally speaking, right, you have free functors are adjoint to forgetful functors. So it's very common. It's very common for there to be an adjoint to a forgetful functor. And in the case of going from a category to a groupoid, that's called groupoid completion. That one is well defined, and I believe that you can always do that. Similarly, in the case of going from a groupoid to a topological space, geometrical realization is always defined. So I think that it's the final level of going from a topological space to a geometrical level. I think that's the only one that isn't universally, where there isn't some kind of procedure, there's some kind of categorical limit that's universally available. I need to be clear. I am a musician, so my grasp on this material, it's okay, but it's not 100%. And the other thing,
you seem to be actually quite good at a lot of it. I'm just not. I wasn't sure about some of the points. I really enjoyed your talk, And so I think you assimilated a lot of mathematics that's outside your wheelhouse quite well. I really appreciate that. So, yeah.
Thank you. I appreciate that in turn. Not just when I bring up my being a musician, I'm asking for mercy, but also it is true that like topological spaces, there are a lot of really weird ones, right? And in music, the things we deal with in music tend to be relatively well behaved, and so they admit of. So, for instance, I'm pretty sure that okay, this I believe I can say. So if you start with a groupoid and then form the geometrical realization of the groupoid, you get a simplicial set, and a simplicial set is always metrizable, right? So I think if you're coming from the category to the groupoid via groupoid completion, and from that to a geometrical space, you're going to get a very well behaved topological space that is metrizable, right?
Okay, so when you go back, it's the composition that works, not necessarily the individual functors.
Yes, and
you have to compose functors along the way and pay attention to their ranges. Because,
yes, exactly.
The range of the groupoid one, going from groupoids down back to where is it? To metrizable spaces.
Yeah.
Or metric spaces. That's requiring you to in order to unforget, you must have the spaces that you're working on from the topological category to the metric space category. Those have to be in the range of your functor that you applied previously.
Yes, that's a great point. And I believe that is the only arrow on my diagram that is like that. So the forgetting, I think you can always, it's not a huge problem, the forgetting. Maybe the topological space to the fundamental groupoid, that might also be a problem too. Okay, so the topological spaces are kind of the odd level out. Thank you. I will think more about this, and next time I give this talk, I'll be a little bit better about that. It's a great point about the topological spaces.
Right, and I really like the fact that you were formulating things in terms of equivalence relations and so forth. You mentioned fibers, and your discussion of fibers in terms of the identity does not ring a bell for me, but I would have to think about it. My familiarity with fibers is more function theoretic rather than category theoretic. I know they're talked about in categories. So to me, my experience with the terminology about fibers is that the preimage of a point under a function is the fiber of that point under that function. And so I don't know how that translates into what you said. So I'll have to look that up.
I mean, it's almost the same. If you take the point to be an object, and so the preimage, if you take the point to be the object with its identity, then what you just said is it's the preimage of the fiber of an object if you have a category theoretic functor, the fiber of any object in the base space is the preimage of the object with its identity.
Okay.
That one I'm pretty confident.
Yeah. Okay. Okay. That kind of fits.
And the bigger the fiber, the more information you're absolutely discarding, right? That's the key intuition there.
So now I have a more music-related question. One of my favorite composers is Bela Bartok.
Okay.
How does his music fit into your scheme?
Right. Okay. So there's a general. So Bartók is a great composer. Bartók is in this generation who grew up like Stravinsky and Debussy. He grew up learning the old language of tonal music, and then was sort of, as an adult, was freed into this world where you could sort of experiment with and invent your own grammar. And Bartók wrote in many different styles, and so he has a more accessible style, and then he has a more avant-garde atonal style, and sort of he would go back and forth between those different modes kind of through the course of his life. What I would say is I believe so. As a general rule, I believe that 20th century composers faced a challenge of inventing a new musical language, trying to generalize the grammar that they learned as children, the tonal grammar, trying to sort of distill its core principles and let's say remove the arbitrary conventional features of that language. My general belief, and it's difficult to say this, is that they did not do a great job with that project on the conceptual level. They wrote great music. Many of them were very intuitive, but I actually think that, like, in terms of understanding the logic of that earlier language, that's a really hard problem. That's a little bit like you could think of it as the analog of coming up with the grammar of a natural language. And if you want someone to come up with the grammar of a natural language, you should not ask a poet, because that is not their strong suit. Poets are good at absorbing and transforming a language. So I actually think there are basic properties, like the one I talked about the dependency relationships and stuff. We should have known that in 1911, and it's wrong that I'm pushing on this and that it's relatively new stuff in 2026. That should have happened 100 years ago. So I would say, I think the history of music might have gone differently and might have been a little more interesting if we'd hit on certain deep core principles a long time ago. And again, Bartók is a great composer. Stravinsky's a great composer. Messiaen, Steve Reich. There's a lot of great composers, but it is astonishing the degree to which they were flying blind. It is astonishing, and it is depressing when you compare their music to Brahms or Bach or Beethoven. Those guys had real structure in their music, and there's a kind of hierarchical richness, a kind of analyzability, a structural richness that when you get to even the greatest 20th century music, there's a lot more seat of the pants kind of. I'm just going to put this note. I'm going to put a weird note in here just because it sounds cool. And so I think we're really not even at a level where we can understand what that means aesthetically. It's kind of new territory.
So very close to my heart is the discussion of poetry there. A part of music that is, I would also like to see perhaps how you would treat rap and other modern musical styles that are spoken word type music that is basically poetry adapted to a more rhythmic performance rather than just written on a page for people to read. On the other hand, someone like E. Cummins, who, like you said, he knows grammar. He has to be a good poet, but maybe he's not a linguist. Maybe he doesn't deal with the logic of the structure of natural languages beyond the point of making the musicality of the written word and spoken word. And I've got a recording of him reading one of my favorite poems he wrote called "Anyone Lived in a Pretty How Town," and I have performed it at open mics in this area, and my performance is very different than his. And I had done it several times, and then I got this recording later, and I thought, wow, why does he do it that way? So I guess to some extent, I would love to learn more about how you would analyze things like that using your approach, even though your approach is more, from my perspective of what I've seen, it's more for the music that is composed with notes and so forth, and with various tones, rather than spoken word type performances and so forth, and performance art.
Yeah, okay. So there's a lot in there. I'll just say very quickly. So, I'm a big fan of popular music, of rap, jazz. I don't think composed is that relevant. One of my favorite 20th century musicians is McCoy Tyner. I absolutely love McCoy Tyner's playing. He is doing a lot of this stuff. One of the things that's really interesting about jazz is jazz musicians, instead of abandoning the tonality of the 19th century, they adapted it, right? And so it's a living tonal tradition, and there's a lot of incredibly, that stuff is in my wheelhouse in terms of analyzing it.
Okay.
The thing I would say about rap is there's a lot of music in rap, right? Like from my point of view, rap is very similar to other kinds of popular music. It's got chord progressions, it's got verses, it's got choruses. It's just that instead of a sung melody, you often have a spoken melody, right?
Right.
So there's a very complicated story to tell about essentially the quotient I was talking about, where you take pitches on a line and then you form a circle where you mod out by the octave. You can do that where you replace pitch with time, and that instead of the octave, you have the measure. So 1, 2, 3, 4, 1, 2, 3, 4. That's a circular structure in rhythm. So a lot of the same math. Now, a lot of the same math also applies in the rhythmic domain. Now, there are some differences, but the differences are subtle. So there's and then there's some interesting perceptual differences. So, but there is a whole. It's analyzing pitch is maybe what music theorists do. Sort of, that's their easiest and most common occupation. But rhythm, there is a whole subfield of rhythm and thinking about.
Of course, yeah.
So if you gave me a piece of rap music and I was, tasked with analyzing it, I would think very carefully about the rhythm. And one of the things that's really interesting in rap and in rhythm, in pitch, really, well, in rhythm, we have these micro deviations, right? Like being a little bit ahead of the beat, a little bit behind the beat. And so that's a fascinating, being a little bit sharp of the note or a little bit flat. You can glide to the note effectively, but if you're too flat, if you're consistently flat, that kind of sounds stupid. But if you're consistently behind the beat, that can sound very cool. And so I would say there's more richness in the microstructure of sort
nuance and richness, and
the grid plays a different role. Yeah. The other thing is speech has pitch in it, right? And so if you look at like phonologists, they talk about intonational contour, and so even in the spoken parts of rap, there is a pitch level that it's not melodic and but you sometimes see people notating pitch contour as a way of getting at the intrinsic musicality of the speech. Oh,
And then
one
I
final
had,
thing, just one more
yeah.
thing, but before you Google speech to song illusion. Just when you're done here, Google speech to. There's an amazing phenomenon where if you take speech and you just repeat it enough, you start to hear it as melodic, and it's really mysterious, and it's sort of universal.
Part of the basis of poetry in the first place is
that
you can do that. And so now a more technical thing, if we still have time. I know if probably a bunch of people are ready to leave.
Matt, but okay.
But so are you familiar with Leslie Lamport's temporal logic of actions?
No.
So he
sounds like it should be.
So he developed this for computer science, for distributed systems. Where timing is very important in terms of communication between processors. So your discussion about the philosophy of time, of not time, but of space and location and time, all made, and your discussion of Leibniz and Newton's disagreement made me think of this. And in relation to your approach, your category theoretic approach with all the quotients and so forth, that in some sense, the notion of absolute time in temporal logic of actions is captured by vector clocks, because time is not just a number, it's all the perspectives gathered together in one vector of the whole system in a given communication stream, or an instance in a communication stream. So if you take your different, so you take a structure that's got the most fine information, the geometric structure, right? I think that's what you consider the most fine approach to music, and then you quotient, or you forget that you do the full functor and you go to the topological space. You forget the metric. So you've got there two different notions, and if you think of a processor holding the metric information, and then a processor just holding the topological information, and then another one for the next level, and another one for the next level, and then you put those all in a vector, that's sort of your absolute time in some sense, or your absolute space. I think that might be a useful way to think of it. And especially if you're doing programming, because you can have one processor for your music that's doing things in the geometric sense, and then another processor applies the forgetful functor to that and works on the topological information, and they communicate with each other.
Right.
But when they send a communication, you want all the processors in your distributed system to have a vector of the information that all the other processors want them to have at that given instant. And I think that would be a useful thing for you to get some students to build in. I know you probably don't have time to do it yourself, or get some collaborators to try to build into there. Someone who in computer science knows about Leslie Lamport's temporal logic of actions.
So let me just this is all very interesting to me. One thing that I'm really interested in is Western musical notation kind of forces a universal time like literally just to notate things in Western notation, you have to choose where the downbeat is, you have to choose where the bar lines go, so you have to choose the time signature and all this stuff, right?
Right.
And there are a lot of musical styles, particularly African musical styles, where different performers can disagree about where the downbeat is. So there's a wonderful article about a kind of marimba music where two players play the same melody in a very fast pocket. So they're one right after the other. And it's almost impossible to do. And the way they do it is each player thinks of themselves as playing on the beat with the other guy playing the wrong beat, right? And you just can't notate. So you can't notate that in Western music. And what you said is really interesting to me, because each of those players has a conception of where their notes are and where the other person's notes are, but those conceptions don't line up. They're not the same, right? And so this idea of multiple temporalities is one that, and I will just say, so if you guys are interested, a student and I, we have a project called Harmonia, which is a kind of builds some of these ideas into the DAW. And I think a very deep concept is people think of a score as a mapping between symbols and actions. So you see this dot, you play this note, right? And a much richer way to think of the score is it's as a mapping between scores and a kind of master score. So this score here is a pattern or a motif or an idea or a melody. And then the score is actually projecting this thing at multiple places. A single object appears within the master score in multiple different ways. And in that case, you have an internal temporality and an external temporality, and you have all of this stuff that you're talking about. And so
the communication of the temporality of individuals and of the system is communicated to the individuals and the through the music.
Yeah,
and so that in the African music setting you're describing, that's what I understand is that it's communicated through the music.
I have
all right. Last question, and then we're going to go. I gotta have lunch.
Of course, yeah.
Question: how does the logic of this situation that you're describing with the different modalities of music in different cultures force an expansion of an ontology? It seemed like that question.
Right. Well, in this case, so this is a huge problem. So I think that if you look very broadly and zoom out, right, kind of a deep history point of view, the 20th century saw a tremendous kind of multicultural trade of musical ideas. And generally speaking, pitch ideas flowed from the West to other cultures. So if you go to any country on earth, you can turn on the radio and hear chords and melodies that resemble Western pop music chords and melodies. Generally speaking, rhythmic ideas and percussion ideas flowed in the opposite direction. So the idea of having a drummer play all the time in your music is completely foreign to Mozart or Bach or Haydn, and yet is incredibly characteristic of, South Asian music, lots of the world's music, right? So generally speaking, the West gave the rest of the world chords and harmonies, and the rest of the world gave the West the drum set and all of syncopation and polyrhythm. And so what I would say is we are still coming to grips with this massive, ontological gumbo, and it's a real problem. Look, if you go to a conservatory, if you go to a place like Juilliard, right, or Curtis, they are teaching people to notate string quartets, and they're maybe not grappling with this new ontology of music that involves drums and involves, electronics and in some sense, the oh yeah, I didn't mean to say that I didn't mean to say that that there's
the
no
Indian,
pitch
the
and
Eastern, truly
no,
Eastern,
but
Ravi
there are
Shankar and
things.
so forth. Yeah, and
The
then
idea
even
of
more.
modulation, the idea of changing the scale in the middle of your piece, right, which is kind of the bread and butter of Western music. That's pretty foreign to traditional South Asian music, right? Like modulation and chord changes that happen quickly. Anyway, this is a long story, but we were. So I'm not trying to say that there's no pitch ideas. It's just, if you look very generally, there is this sort of two-way cross-pollination, and so I think we're still struggling.
2 or 3 more. Maybe you have 2 or 3 more relatorium seminars you can give us.
I know.
All right.
Well, Dmitri, this has been fantastic. Thank you so
Thank you so
much.
much.
It's wonderful. Thank you, Dmitri.
Yeah.
All right. Yeah. Thank you guys for listening. I really enjoyed it.
Enjoyed it a lot.
Good luck with your projects.
Thanks. Bye.